The question, so who of you ever went through this hassle of spending hours and hours in Excel cleaning data? Yeah, thanks. That's what I tried to solve using methods similar to what Lasita did. So my name is Alex Donkers, PhD candidate at Eindhoven University of Technology. Let's start. So the work basically started from this notion of digital twins, where we have real-world components where we monitor data to update virtual representations, and then collect insights there to maintain the real world again. And there are many benefits of this idea, but one of them is that we can now apply artificial intelligence in this virtual representation, making better decisions, wasting less resources in the real world. But in order to do that, we need good data in this virtual representation, and it's totally a mess currently. Yeah, we try to clean stuff. The static BIM-ish information, we typically describe this using semantic web technology, so we convert these current data silos into graphs. The nice thing is that we can easily describe relationships in these graphs between objects, and we can also convert other data silos into graphs, integrating them. This has been work for decades now, and I think that many of us agree that this is relatively structured and we can maintain data quality there. But then there's time series data, and this goes so quick, and it's as we just saw, it's relatively messy. It's impossible to maintain quality in this kind of data by hand. So we need automated methods. And the idea of this paper is, can we use this thing to clean this thing? That's basically what we're doing. Or in a more academic sense, what is the potential of using semantic web technologies in the data preparation or data cleaning phase? And we did three things. It's basically a hands-on experiment that we did. It's not finished. What values are missing values, what values are outliers, and if we detect them, how can we replace them with something that is possibly correct? As a basis, we created this thing called semantic digital twin. So we have this model which is open family home. Everything is available in GitHub. So we converted this thing to RDF. We converted weather data to RDF, sensor data, or at least the metadata of the sensor, and the metadata of IoT devices. And enriched it even with dbpedia data. So this is how we structured our models. This is a snippet of it, basically the experiment. So what you see here is a room with 5 sensors. Those are the 5 circles, 3 on the table and 2 on the wall on different heights. These are luminance sensors. Then we structure the topology of the building in green using the bot ontology, and we enrich it with dbpedia data to give it some context. And we have relatively extensive, this is just a snippet, relatively extensive metadata of the sensor. So we see luminance sensors, and we basically convert the entire data sheet of the sensor. So what is the frequency that it measures in? What is the resolution of the measurement? What are the minimum and maximum values that it can measure? We represent everything in RDF. So the framework of cleaning is then this. So we have a lot of data. We convert that to RDF, and for the sensors we only convert the metadata to RDF because we store the real raw data in InfluxDB. We then query relevant metadata using Sparkle. For example, where we store this time series data in the graph, but also, for example, this minimum and maximum range and the frequency and the resolution. Then we insert the results of that Sparkle query in a Flux query, which is a time series query. And Flux has these filter options. For example, we can filter values on minimum and maximum range. And then we use that Flux query to query data in Flux and have clean data that we can then use somewhere else. So the idea is that we clean the data in the querying process instead of after the querying process. So how can we then detect missing values? Different options that we tried. First of all was a null value representation. So in databases, that's it. Mike? A representation of a null value that is no data or none or null, and it's always different. So we store this in the graph, we can query it, and then we can filter in our influx queries points that have this
basically this null value, and then we can filter them out. We can also do a little more complex stuff. So we have this frequency value, so we know the frequency of measurements, and then we detect whether there is a gap between two time series measurements that is larger than this frequency, and if it's larger than twice the frequency, we know that there's a missing value in between. So if there's a too large gap. We can detect outliers using basically explicit information, which is that product data sheet. So sensors come with a minimum and maximum measurement range. For example, a temperature sensor measures between -10 and 70 degrees Celsius or so. So we can represent that in the graph and basically filter all the values in our query that are either lower than the minimum or higher than the maximum, because they cannot exist. But yeah, so we created this data set, and you can see that these values are basically too wide, so we would still have messy data. So we also tried implicit ranges. Here we insert kind of a custom range based on the context of the sensor. So in this case, we know that the sensor is a temperature sensor because it measures temperature in a house in the Netherlands, in a kitchen as well. And we know, based on experience, this is domain knowledge, that this sensor then, for example, should not have a value lower than 10 or higher than 30, because that's very unreasonable. So we insert then these custom ranges, and then basically these ranges there get smaller so that we can also get these outliers that we couldn't get through the object, through the sensor data sheets. And yeah, there you can see how you then filter this in Flux. So if we detect these things, how can we replace them? What we did with these 5 sensors is we used a prediction-based semantics indexing. So we create vector representations of the sensors in the graph and their relationships. So it's purely based on semantics. And then here we ask which sensor is the most similar to the sensor 1, which is the left one on the table. And then obviously sensor 2 was the most similar. So we then used the values in sensor 2 to replace values in sensor 1 using multiple ways. That's them. So this is the sensor data from sensor 1. We manually delete this part. What you then, for example, can do in regular methods is linear interpolation, but you can see that this is not what we want to have. So we did multiple tests. First we did the semantic similarity. So we just took the sensor data from sensor 2 and imputed it in sensor 1, which is the green line, which is way better than the linear interpolation, but it's still not as good as we would like to. So then we had this semantic shape follower methods, where we used the deltas of sensor 1, so the changes in the sensor data, and with the starting point of sensor, the delta of sensor 2 with the starting point of sensor 1, and you can see that the pink line almost exactly follows the actual data. So we don't know the data of sensor 1, but we can actually model it through the data of sensor 2. And we had multiple imputation. That was very bad because of we basically combined the 3, but that was very bad due to the linear interpolation. Okay, discussion. Yeah, it was a hands-on experiment, and this is highly context specific. So we now did a kitchen in the Netherlands with a temperature sensor. You can imagine that we need to create these rules for basically every situation. I believe it's a nice thing because we can create very domain specific or local rules. So companies can create these rules. We don't give any insight in the similarity scores. So we now just took the best one, but we tried it for temperature sensors and for luminance sensors, and for a wider range. And there's always different similarity scores that pop up, and we don't really know which is the value that is acceptable. And we also don't give insights in why certain sensors show outliers or missing values. And I think that this is maybe next stage. So if we can extract these data quality metrics and feed them back into the graph, we might actually be able to inform facility managers or so to find the root cases of failing systems. So to conclude, data preprocessing is boring and time consuming. I believe that semantic representations of buildings can enhance the preprocessing tasks, and the semantic models have the potential to enhance AI systems in a broader sense, I think, to deal with this context specificness of AI systems in the built environment. And with that, I'd like to thank you very much and hope that you have some questions.